In the world of computer science, we often encounter problems that are not linearly separable. Picture this. You're tasked with classifying images of cats and dogs, or perhaps you're trying to predict the sentiment of a piece of text. These tasks are not as straightforward as plotting points on a graph and drawing a straight line to separate them. No, they're much more complex. Take image recognition, for example. The features that distinguish a cat from a dog are not simply a matter of height or weight, but involve intricate patterns and shapes that a linear model just can't grasp. Or consider text classification, where the meaning of words can change based on context and the order in which they appear. A linear approach just won't cut it. These problems require a model that can handle their complexity and nuance. This is where the concept of nonlinear support vector machines, or SVMs, comes into play. Nonlinear SVM classification offers a solution to these complex problems. To understand nonlinear SVM classification, let's first understand what SVMs or support vector machines are. SVM is a supervised machine learning model used for classification and regression analysis. It is built on the concept of hyperplanes, which are decision boundaries that help separate given sets of data into different classes. This works well for linearly separable data, which means that the data can be divided into different classes using a straight line. But what happens when the data isn't linearly separable? That's where the magic of nonlinear SVM classification comes in, with a little trick called the kernel trick. Imagine you're trying to separate apples from oranges, but they're all mixed up in a fruit bowl. A straight line can't separate them, right? Now imagine if you could pick up that bowl and shake it until all the apples are on one side and all the oranges are on the other. That's basically what the kernel trick does. The kernel trick transforms the input data into a higher dimensional space. In this new space, the data that was previously all mixed up becomes linearly separable. This is like shaking our fruit bowl in a third dimension, allowing us to separate the apples from the oranges more easily. This transformation is done using a mathematical function known as a kernel function. There are different types of kernel functions, such as linear, polynomial, and radial basis function, or RBF, each with its own strengths and weaknesses. The choice of kernel function can have a significant impact on the performance of the SVM classifier. By transforming the data into a higher dimensional space, nonlinear SVMs can find the optimal hyperplane that maximizes the margin between the different classes. This margin is what allows the SVM classifier to make accurate predictions when new data is introduced. So, in the realm of machine learning, when data doesn't play nice and align itself in a linearly separable manner, we turn to nonlinear SVM classification. By using the kernel trick, nonlinear SVMs can solve problems that linear models cannot. There are several key points to remember about nonlinear SVM classification. Firstly, the kernel function plays a pivotal role in nonlinear SVM classification. This function is responsible for transforming the input data into a higher dimensional space where it can be more easily separated. The choice of kernel can drastically affect the performance of your model. Commonly used kernels include polynomial and radial basis function, or RBF. The polynomial kernel, as the name suggests, creates a polynomial of the original features and allows for a more complex decision boundary. On the other hand, the RBF kernel is a popular choice due to its flexibility. It can create complex regions within the feature space where instances of the same class are likely to fall. Secondly, understanding the trade-off between model complexity and overfitting is crucial. A complex model with a high degree of freedom may fit the training data very well, but it can also lead to overfitting, meaning it won't generalize well to new data. Conversely, a simple model may not capture all the nuances of the data, potentially leading to underfitting. Striking the right balance is key in building a robust and effective model. Another important aspect to remember is that SVMs are sensitive to the choice of parameters. The cost parameter C, for instance, determines the trade-off between achieving a low error on the training data and minimizing the complexity of the model. A large C will classify the training examples with high accuracy, but may result in a complex decision boundary, prone to overfitting. Finally, to select the best parameters for your SVM, cross-validation is a useful technique. By splitting your data into a training set and a validation set, you can train your model on the training data and then test it on the validation data to see how well it performs. With a good understanding of these key points, you can effectively use nonlinear SVM classification to solve complex computer science problems.